Good morning, students. Myself, Dada P, Assistant Professor, Department of CSE, B.A. Ballari. Today, I'm here to give a lecture on verification and validation of simulation models under the course System Modeling and Simulation. So, let us begin with the topic Introduction. So, one of the most important and difficult tasks faced by a model developer is the verification and validation of the simulation model. Once the modeler has developed the simulation model, he needs to verify whatever the model has been developed is correct, whether it is performing the expected functionality or not. The model developer should work closely with the end user throughout the development and validation of the model to increase the credibility of the model being developed. The goal of verification process is twofold. The first goal is to produce the model that represents true system behavior closely enough for the model to be used as a substitute for the actual system for the purpose of experimenting with the system. The second goal of verification and validation process is to increase the credibility of the model so that the model will be used by managers and other decision makers. So what exactly verification and validation? How they are different from each other? Already we have seen this topic, that is verification and validation, in software engineering from the fourth semester or third semester. So verification is concerned with building the model right. It asks the questions: is the model implemented correctly in the computer? Are the input parameters and logical structures of the model correctly represented? Whereas validation is concerned with building the right model. It is utilized to determine that a model is an accurate representation of the real system. It is usually achieved through the calibration of the model. The calibration we'll see in the later topics. Calibration and validation both are one and the same. The thing is, calibration is one step in validation. So these steps are continuously repeated. The calibration is done for n steps. Once the modeler is satisfied with the calibration, that will become the final validation. So there are four important topics in this module, in this chapter of the module. The first topic is model building, verification and validation. Topic 2, verification of simulation models. Topic 3, calibration and validation of models. And topic 4, three steps validation approach by Naylor and Fincher. Dear students, these are the four important questions which are going to appear, which will be appearing in your final exams, your external exams. Sometimes all the four topics will be asked for 4 marks each. Sometimes three topics will be asked. If they are asking three questions, like the first one, second one, third one, it will be for 6 marks each. Sometimes only two topics will be asked out of these four. Two questions will be there. So that if that is the case, each question will be for 8 marks. It depends. But these are only the four important topics in this chapter. If you completely study this without leaving anything, so you are going to get one complete question from this. So let us see with the first topic, that is model building, verification, and validation. The diagram clearly shows the model building, verification, and validation approach. If you look at the name is model building, verification, and validation. But in reality, first we do validation, then we do verification, then finally we build the model. So what exactly these steps are? So it is very clear from the diagram. So you can observe the first thing what the modeler does is the modeler observes the real world system. So it's very much clear. The modeler observes the real world system. After observing the real world system, he tries to construct the conceptual model from this, right? So this process, when he observes the real world system and he constructs the conceptual model, if it is very much clear in the diagram. You see this is what conceptual validation. This is the validation process that we will see in detail later. So after constructing the conceptual model, then he constructs the operational model. So that The phase from which the conceptual model is converted to operational model is nothing but model verification. So finally, when it gets the operational model, that itself is our final, that is model building. So if we look at validation is done first, is just you can check out. The second one is verification, and finally the model building. Model building is this step. So what exactly is this one? So the first step, what is the first step? That is observing the real system. You can see this diagram. Real system is there, and there is a circle there. That is an activity. So the first step, observing the real system. In the first step, the model building consists. The first system of model. The first step in model building consists of observing the real system and the interactions among its various components and collecting data on its behavior. That is, various components can be like operators, technicians, repair and maintenance, personnel, engineers, supervisors, and managers. So let us see this diagram. So what is does first? The modeler observes the real world system. After observing the real world system, now let us see the second step one more time. The second step, the modeler constructs the conceptual model. It's very much clear from the diagram. Keep this diagram in mind. So while constructing the conceptual model, these are some three important points what it does. So in the construction of conceptual model, assumption on the system components has been done by the modeler. Then it does structural assumptions which define the interaction between the system components. The third important thing what it does is input parameters and data assumptions. So all these things constitute the conceptual model. So that's the same thing what I have spoken just now. The conception of conceptual model, the modeler assumes or collects assumptions on the components and the structure of the system, plus hypotheses on values of model input parameters. So as illustrated in the diagram. The third step, let us go back. The third step is, so once the conceptual model is constructed, now it has to be transferred to the operational model. That is what computerized representative model, right? This is actually the model verification. So what exactly it does there? How exactly he construct that itself constitutes model verification. So this process is repeated until the modeler is satisfied with the model being produced. That means the model whatever is being produced has to closely reflect the real world system in all its functionality. The second important topic, as I said, is the verification of simulation models. Students, please keep this diagram all the time in mind to answer all the topics. So now the second topic being discussed is verification of simulation models. So it's very much clear from this diagram. Verification, I said, it's here. That means what? We are converting the conceptual model to what? Operational model. Simply speaking, verification is this much. So now what exactly verification in detail? The purpose of model verification is to assure that the conceptual model is reflected accurately in the computerized representation. As I said, it's very much clear from the diagram. We are converting the conceptual model to computerized system. That itself is verification. This part. Okay. So the conceptual model quite often involves some degree of abstractions about the system operations, right? So for this abstractions, so if you want to get in light what exactly how we should get these abstractions to reality, what we can apply, what knowledge we can apply depends upon the modeler, and many common sense suggestions for verification process can be given, such as the computerized representation checked by someone else other than its developer. So the modeler can even make a flow diagram which includes each possible action a system can take when an event occurs. The modeler can closely examine the model output under a variety of setting of input parameters. Whether the computerized representation prints the input parameters at the end of the simulation to make sure that these values are not being changed inadvertently. Make the computerized representation of self-documentation, another important point. If the computerized representation is animated, verify that what is seen in the animation imitates the actual system. That means your animation, whatever you're representing, should be the same what the system is behaving. You should animation should not be something else, and the model should not be something else. If you want to increase the readability. The seventh point goes like this: graphical interfaces are always recommended for accomplishing verification and validation process. Eighth point: see, even the best of the simulation analyst makes mistakes, because it's an art. Building a model is an art. It requires a lot of skills, right? So even the best of the simulants can make mistakes or commits logical errors when building a model. For this purpose, the modeler can use a debugger or interactive run controller, right, which is an essential component of successful simulation model building. So how exactly IRC helps the modeler? IRC assists in finding and correcting those errors in the following ways. The simulation can be monitored as it progresses. Attention can be focused on a particular line of logic or multiple lines of logic that constitute a procedure for a particular entity. Values of selected model components can be observed when the simulation has paused. The current value or status of the variable, attributes, queues, resources, counters, all those things can be observed. The simulation can be temporarily suspended or paused, not only to view the information but also to reassign values or redirect entities. So, students, this completes the second topic. Now, let us go to the third important topic, that is the calibration and validation of the models. So, if you look at the diagram, what has shown already here, the calibration and validation word is there on the left side. Actually, calibration is a part of validation. It's like ith step. It's like an ith step in n step. So here, if you see on the right side, it is only validation. To achieve validation, what we do calibration. So let us go to the topic. So although verification and validations are conceptually distinct, usually they are conducted simultaneously by all the modelers. Okay. So apart from that, validation is the overall process. As I said already, validation is the overall process of comparing the model and its behavior to the real system and its behavior. Whereas calibration is the iterative process of comparing the model to the real system, making adjustments to the model, comparing again and so on until the model is satisfied with the model being produced resembles the real system. Right? As shown in the next diagram, that is the figure 2, the relationship of the model calibration to the overall validation process. Let us see this diagram. It's very much clear from this diagram. So, in the initial step, the modeler observes the real world system, and after observing the real system, he tries to build an initial model. After creating an initial model, the modeler compares the initial model with the real world system. If he is not satisfied with the working of the initial model, that means the initial model, if it is not resembling the real world system in its functionality, in its way of doing work and all those things, then he will revise. He will revise the things and he will make corrections, he will make adjustments. Then he will get a first revised model from the initial model. Again, this first revision of the model is compared with the real world system, right? So if he's satisfied with the first revision of the model, if he thinks the modeler thinks that the first revision of the model is resembling the system, what he wants, the important functionality, then this first revision itself will become the final system. If not, again, you'll get the second revised model. That means he again goes with some changes after comparing the real system, make the adjustments, again compare, check the real system. This process goes on, goes on until the model is satisfied with the model. So it's an iterative process, right? That's why if you see the diagram, it is labeled as iterative process of calibration of a model. Iterative process of calibration. That means what? In each step, every time validation is done, that each step is called as calibration. These steps are repeated until we get the final step. That is the final validation. That means calibration is a part of the validation. It's like an ith iteration. It's ith step in nth step of a validation. Okay. So, as I said already, the diagram resembles the overall process. The comparison the model is reality is carried out by various tests. The test can be subjective or objective. What are subjective tests? Subjective tests usually involve people who are who are knowledgeable about one or more aspects of the system. They may give some suggestions. The inputs can be taken from them, and then the modeler, while making an adjustment, he can, while comparing the model with the real world system, he can make adjustments by taking the inputs from these knowledgeable people, and again he can just try with the model. The next objective test may require some data on the system's behavior plus the corresponding data produced by the model. Yeah, that completes the third important topic. Now let us see the fourth important topic. As I said, there are only four important topics in this, and there will be four questions, four straightforward questions in your external exams. The last topic for this in this chapter is three-step validation approach. This is a quite common asked question in video external exams. This three-step validation approach is been given by Naylor and Fincher in the year 1967. So as the name itself suggests, it is a three-step validation approach. There are three steps in this. The first step is to build a model that has high face validity. The second step goes like this: validate model assumptions. The third step is validating input-output transformations. Validating input-output transformation. That is to compare the model input-output transformation to corresponding input-output transformations for the real system. So let us see the first step: building a model that has a high face validity. So this is the first goal of the simulation modeler, is to construct a model that appears reasonable on its face to the model users. Reasonable in the sense the model should resemble real world system. The, the people who use the model should be confident enough that it is serving the purpose of the real world system, right? Then only the knowledge of the real world system being simulated, the people will have confidence to use this model. If it is not reasonable on its face, it is not having high face validity, definitely the model will be rejected by the users, right? While building this model, the most important point is the users of the model will be using the model should be involved in the model construction from its conceptualization to its implementation until the final step, right? This has its own advantages that I will be discussing in the next slide. The model builder must attempt to choose the most critical input variables for testing. Why means sometimes it is very much difficult. It might be time consuming to check with all the parameters, all the values. So at least, or the most important point is the modeler must attempt to choose the most important variables, the most critical values for testing the model. So as I said, the second point is the user of the model should involve in the model construction. So what are the benefits, what are the advantages of involving the user from the conceptualization to implementation in model construction? The advantages goes like this: the advantages of user involvement. Uh, High degree of realism can be achieved. That is, high degree of realism is built into the model through reasonable assumptions regarding system structure and reliable data. The second advantage, it increases the model's perceived validity or credibility, without which managers will not be willing to trust simulation results as the basis for decision making. Third one, sensitivity analysis can also be used to check models' face validity. Sensitivity analysis, so varying the different parameters, checking the results, varying the input, checking the results, giving different load on the model, checking how it will behave. All this comes under sensitivity analysis. The fourth important point, the model user is asked if the model behaves in the expected way when one or more input variables is changed. That means that's why the user of the model is required to be there. He has to be involved in the complete process, because if he is the person who is going to use the model, and at the time of construction, during the time of building the model, if you change the input parameters and if you see the output, he will be the best person to tell, yeah, the system, whatever the system behavior is correct or not, it is not behaving properly. So as I already spoken about the fifth point, sometimes what happens, it will be too expensive or time consuming to vary all input variables and say, then at that time the model builder must choose the most critical input variables for testing. The step 2 of the three-step process of the by Naylor and Fincher goes like this: validation of model assumptions. So normally the model assumptions falls under two general classes. The first class is structural assumption and the second class is data assumptions. So structural assumptions involve questions of how the system operates and usually involve simplification and abstractions of reality. For example, if we take a bank database or a banking system, not a database, banking system, how exactly the banking system, the bank system has its own structure. For example, customers has to stand in queue. It will have a queue. What is a queue? Whether it's a FIFO, normally it is a FIFO queue. And service facility. How many services is there? How many servers are there? Who is going to provide the service? All those things. These are all under comes under structural assumptions. When the model is trying to build the model, you should be assuming what the structure of the model is sometimes, right? Because all the things will not be known in the first step. You need to assume something. You need to assume, well, the queue is there, how the queue should behave. Normally the queue will behave first in, first out. The person who has come first, he has to be served first. That is the way. But sometimes possible in different scenario, the queue behavior or the queue structure might change, depends upon the model and depends upon the situation what he is modeling. The second is data assumptions. Data assumption should be based on the collection of reliable data and correct statistical analysis of the data. So correcting collection of reliable data, correct data, the required data, the necessary data, and even after collecting that, there should be correct statistical analysis has to be done. The statistical analysis part, there are different methods that we are going to see in the coming modules. So there are some of the things here when the data when is collected. For example, for a banking model, we can think of interarrival times of the customers during several 2 hour periods of peak loading, that is a rush hour traffic, interarrival times during slack period, service times for commercial accounts, service times for personal accounts. All those things can be assumed. Like he can be, the modeler can think of all those things. Look, I need to assume this. I need to assume this. You need to model all those things, right? And the process of analyzing the data consists of three steps. Because as I said here, it is there. Correct statistical analysis of the data has to be done. So statistical analysis consists of normally three steps: identifying the appropriate probability distribution. Probability distribution normally ranges from 0 to 1, that we will see in the next module. And the second point is estimating the parameters of the hypothesized distribution. This also will be going to see in the next module. What is the hypothesized distribution and all these things. Third, validating the assumed statistical model by goodness of fit test. So whatever the model we have assumed, whether it's valid or not, we need to model that. We need to check that. So that we can do using goodness of fit test. So there are basically 2 to 3 goodness of fit tests, such as chi-square test, Kolmogorov-Smirnov test, and there are also methods from various graphical methods that we'll see in the later models, coming models. Okay, after completing this three-step validation process, that is the second step of the three-step validation process, the third step goes like this: validating input-output transformations. In this phase of validation process, the model is viewed as input-output transformation. That is the model accepts the values of input parameters and transfers these inputs into output measures of performance. This is checked here. It is this correspondence actually that is being validated. Validation in the sense we are actually validating this correspondence. After taking the input parameters, whether this input parameters once they've been processed, whether this parameters has been transferring into the correct output performance measures or not. That's the thing what we are validating here. The second important point in this is instead of validating the model input output transformations by predicting the future, the modeler may also use past historical data which has been served for validation purposes. That is, if one set has been used to developing and calibrating the model, it's recommended that a separate data set to be used as final validation test. That we will see. The accurate prediction of the past may replace prediction of the future for the purpose of validating the future. Yes. A necessary condition for input output transformation is that some version of the system under study should exist so that the system data under at least one set of input condition can be collected to compare the model prediction. Now, is the system If the system is in planning stage and no system operating data can be collected, complete input validation is not at all possible. Complete input output validation is possible only when the required data is collected and the required data is available. So validation actually increases modeler's confidence that the model of existing system is accurate. That is actually the purpose of validation. This is important. Changes in the computerized representation of the system can range from relatively minor to relatively major. This some of the changes can include like this. They may include these things. Minor changes of single numerical parameters such as speed of a machine, arrival rate of customers, etc. These are all minor changes. And minor changes of the form of a statistical distribution such as distribution of service time or a time of failure of a machine. Major changes in the logical structure of a subsystem such as change in the queue discipline. Queue discipline, as I said, first in first out or last in first out or priority based, whatever it is. That if logically if it changes, definitely the change will happen in the model. That this change can be taken as a major change for the waiting line, or even change in the scheduling rule for a job shop model example. Major changes involving a different design for a new system such as computerized inventory control system replacing a non-computerized system. Yes, these are under major changes. So as we said, input output validation can be done using statistical data and using historical input data. So input output validation using historical input data technique involves usually generating artificial data, right? Usually artificial data generated is taken as an input data for the model being developed. While using artificially generated data as an input data, modeler expects the model to produce event patterns that are compatible with the event patterns that occurred in the real system during the period of collection. If these patterns are compatible, then only the modeler will have the confidence whatever the model is behaving or the input output validation is being happening is correct. For example, if you take a bank model, if you take an artificial input data represented as x1 n x2 n, where n is equal to 1 to n for inter-arrival and services time, were generated and replicates of the output data y2 can be compared so that what was observed in the real system and this model both are almost all same. Technique 2, we can also use actual historical record as input data. And this is an alternate method to be used to the actual historical record to derive the simulation model and then compare the model output to the system. To conduct the validation test using historical input data, it is important that all input data, for example, A and SN, and all the system response data, such as average delay or whatever it is, to be collected during the same time period. Otherwise, the comparison of the model responses to the system responses, such as the comparison of average delay in the model to that in the system, could be misleading. An important note here, implementation of this technique could be difficult for large systems because of the need for simultaneous data collection of all input variables and response variables. This is a very important point to be noted. And there is one more process using Turing test also we can validate the input output process. So what exactly is this Turing test? Most of us are familiar with this Turing test. So persons knowledgeable about the system's behavior can be used to compare the model output to system output. So knowledgeable person will come into picture here. For example, suppose there are 5 reports of the system performance over 5 different days are prepared, assume, and simulation output are used to produce 5 fake reports. Okay, for this purpose, the 10 reports should all be in exactly, assume that there are 10 reports out of which we need to identify 5 fake reports. The 10 reports should all be in exactly in the same format and should contain information of the type that manager and engineer have previously seen on the system. Okay, the 10 reports are randomly shuffled. This is just an example, the process of Turing test what I am speaking about. The 10 reports are randomly shuffled and given to the engineers, and they are asked to decide which report is fake and which is real. Because in this process, We are taking the knowledge of the persons, we are considering the knowledge of the person here, those who are already, who are experts like. So if we give this, if the engineers are able to decide, identify the substantial number of fake reports, the model builder questions the engineer and uses, how did you identify this, what knowledge, what basis you identify, and after taking his inputs, he uses this information gained from these people's interaction to improve the model. If the engineer cannot distinguish between the fake and real reports given to them with any consistency, the modeler will conclude that this test provides no evidence of model inadequacy. Okay, this is a type of validation test, and this is called as a Turing test. So, dear students, this complete chapter. If you have any doubts, you are most welcome to put these questions in the Google Classroom, which I have shared the code. Uh, Final message I want to give at the end of this. So, as we know, we are we are in a situation where the entire nation, not only the entire nation, the entire world is facing this the huge problem of COVID-19. So it's all our responsibility to take care of ourselves, take care of others. So please, please, please try to follow the guidelines given by the government. Try to try to stick on that measures. So please don't come outside unnecessarily. Don't be in groups. Take all the hygienic measures what is being suggested. So wishing you all the best, wishing you good luck. So we will continue the this Google class through eShikshana. The next I will going to prepare another next lecture. So till then, take care. Goodbye.